from not digesting their own head to being able to digest their food when they bite a rat or whatever it is they're going to bite. So, and then he also was curious as to what the heck the accessory gland does. And for those of you who aren't familiar, on the little drawing here, you can see the main venom gland, which is the big yellow thing, and then the venom duct passes through what's colored blue in the cartoon, which is the accessory gland, and that sits almost directly above the fang, and it's very small. You can see it if you dissect a venomous snake. You can see the accessory gland. It just looks like a little bit of a thickening around the duct, but it's really not very well understood what it does, but it's there certainly for a reason, so he was interested in that. So if you look inside the venom gland, most of the cells in the venom gland make the venom proteins, which makes sense, right? That's what the gland is there for, is to manufacture the venom. However, a few make hydrochloric acid, and he calls these acidifier cells. So they basically raise the pH, or lower the pH, excuse me, in the gland to about 5.5. The pH in a body is about 7.4, something like that. The enzymes that are part of the venom are actually more active at a higher pH. So basically what you've done by doing that is make the venom gland an environment where the digestive enzymes are not going to be very active. But then as soon as you take that venom and put it into the higher pH environment, it's going to become more active, simply by it's changing the environment rather than changing the venom. So I thought that was pretty interesting. And then the other thing that perhaps the accessory gland is doing, and that occurs inside the gland, the venom gland itself, is these cells that make tripeptides. And there's some other types of molecules that do this as well, but they basically help maintain the stability of the toxins. Because many of the toxins, as I mentioned before, are these really big complex things, and so they have kind of like, almost like something giving it a hug to stabilize it and prevent it from falling apart while it's sitting around the venom gland waiting to be used. And the other thing that I think is interesting is, he pointed out, it's a redundant system. So there are multiple ways in which the venom is stabilized and inactivated while it's sitting inside the venom gland. It's not just one thing. There's several things at work there. So I guess I just thought it was really interesting because, you know, we talk so much about how the venom works and what it does, which is amazing in and of itself, but then look at all this stuff going on just to keep it. I thought that was pretty neat. All right, so this is kind of the last big thing I was going to talk about.
You're getting better.
I am. I worked that time. All right, so Dr. Markland has done a lot of work with copperhead venom, and this is a very short synopsis of his summary of this particular project that he worked on starting in 1982. And what he discovered was this substance called fibrillase, which directly cleaves fibrinogen. And that's good if you have a clot that you want to break up. And he started working with it to try to see if it could be used to break up blood clots in a clinical setting, so for use in actual people. And he did all this work, and I'm not going to explain everything that he did, but he basically did all this work to make it last, so you could store it on the shelf until you need to use it in a patient. It's inactivated by the general circulation, so once it's away from the place where it's supposed to break up the clot, it actually will become inactivated and not continue to break up clots in places where it shouldn't. So that's important. I think you can see why. And the other thing he had to figure out was how to get it into the clot. You can't just inject it into the bloodstream because then it becomes inactive. So they had to work up a delivery system so that it could be put where it needed to do the work. So they did all this work, and they went through phase 1 and 2 trials. I don't know if you're familiar with how the FDA works, but if you want to get a drug approved for use in the United States, it's something like 20 years and so many $1 million, I forget, but it's a very long time. Phase 1 is the smallest, easiest phase to do, and then it gets harder from there. Phase 3 is typically very large clinical trials, and it moved through phase 1 and 2 trials pretty easily, but in phase 3, the results that they were getting were really not as good as what those other phases had shown, And essentially the sponsor, the person, the pharmaceutical company really, who was paying for this research, dropped it. And so the reason that I put this up here is because we talk a lot about, and you hear on TV, you know, the promise of venoms or of other natural products. And here's just an example, not a very detailed one, I grant you, but an example of one person's work from 1982, and he gave this talk last year in 2009. Essentially all this time spent, all this work he put into it, and essentially it's come to nothing as of right now. Now they are still looking to see if there's a way to make it, you know, fix whatever problems they started to get in phase 3, to find another sponsor perhaps. They're still working on it. But I just thought it was kind of an interesting example to show, you know, kind of the trials and tribulations of working with really any biological research, but kind of a good example. All right. Now I think the only other thing I have on here, see, that time it didn't work. There we go. I just put some fun pictures up. So when we were at Venom Week last year, is that right? Last year? Last summer. There's this guy in Albuquerque who has a place called the Rattlesnake Museum. Has anybody ever gone there before? Now, if you go to Albuquerque, I highly recommend it. He has more snake stuff than you can shake a stick at. I mean, he has some actual snakes too, but he's got a lot of stuff. And he has this huge collection of snakebite things, so he brought some of them. And I just took pictures of them because I thought they were neat. I really like the Vac Viper kit myself. And then the other thing I put in here just for fun is I put in a few pictures of some of the babies we had last year. These are baby king cobras hatching out. We had kind of an interesting thing. Our female laid eggs, built a nest, laid the eggs, and when the eggs were hatching, about 2 days later, she started building another nest. And she laid 3 eggs?
She laid 7 eggs, 2 of them were good.
She laid 7 eggs, and 2 of the eggs ended up being good. So that was kind of, as far as we can tell, it's the first known instance of double clutching in king cobras. So that was kind of interesting. But they're really cute when they're babies. This is East African green mambas. And that's pretty true to life colors on them. The one was real dark. These are neat. This is a little Japanese snake called Ovophis okinavensis. Or common name is Princess Habu, just means small viper. Anyway, this is what the eggs look like up here. Now, if you saw those eggs in your corn snake cage, would you be happy with them? No. And we looked at those eggs and we were like, man, I don't know about this. Well, we were sitting there pondering them, and our intern at the time, who had been working on making a label for the snakes to put on their display cage, came up and said, oh yeah, I read about that in the book. They lay them and their shells are really, really thin, and then they hatch in a few days. And so the intern kind of showed us up. And he's right. They lay eggs with extremely thin shells. If you look closely, you can actually see the pattern through the eggshell. And these guys hatched in, what, 5 days? Yeah, and here's baby. And then after they came out, the eggs like totally collapsed. They just looked like little wrinkled up tissue paper. It was really interesting.
You know how long they hold the eggs, long gestation?
I don't know. I don't know. I mean, I would guess about the equivalent of what eggs plus, the incubating would be, but I don't know for sure. It's so hard to tell. I mean, we weren't ultrasounding her or anything, so I'm not sure, but. This is Colette snakes, which are little Australian guys, or big Australian guys. Their color does fade a little bit as they get older, but they still retain some of the red. The female's still pretty orange. And this guy, this is Pumpkin. The egg was laid on like May, 12th or something like that, and it hatched on Halloween. So, which is apparently pretty typical for Gilas, but we just kept checking on that thing for a long time. I think that might be all. Yeah. All right. That's all I have to say. So.